This is lab 4 for the oscillation of a spring. So in this lab, I was tasked with comparing the observed motion of a spring to the predicted motion using a computational model. The two essential fundamental principles in this lab are the energy principle and Newton's second law. Newton's second law, where the net force acting on an object is equal to the mass times acceleration, is important when considering the system as only the mass attached to the spring, with this mass of the spring negligible. The forces we are focusing on are the spring force and the weight force. The other principle, the energy principle, states that energy is not created or destroyed. When considering the energy principle, the mass to focus on is the mass of the spring and the earth, meaning that there are no significant surroundings acting on the system. This means that there is no change in energy of the surroundings, and the change in energy of the system is zero, and what we are focusing on. The essential question that we are trying to answer is if energy is conserved or not, meaning is the energy principle satisfied. For this lab, I was given experimental data to analyze. The given data was the mass of the weight attached to the spring, which was 0.402 kilograms, and the length of the initially stretched spring, which is 0.70 meters. To follow the path and position of the mass, I marked the center of mass of the weight over the time interval, which I started when the mass was pulled to the side at frame 5 and let it run until frame 102, so that the total time oscillating was 9.238 seconds. The essential values needed to be used in the predicted model are the initial position and the initial velocity, which I found from the observed data. The spring constant and relaxed length of the spring are also important. To find the spring constant, I rearranged the formula for the period of oscillation, as well as found the period of oscillation by taking the average of the first 3 periods from the observed position versus time graph. I found the spring constant to be 7.129 newtons per meter and the relaxed length of the spring to be 0.147 meters. This was different from what the calculated spring stiffness and relaxed spring length had been in the lab videos, and occurred because of the differing time frame that I used and where I chose to start my video from, and the fact that the spring moved up and down and back and forth as opposed to just oscillating up and down in the lab video. To create the predicted computational model, I first plugged in my calculated values as well as the observed data. I plugged in the spring constant and relaxed spring length, which is important for calculating the spring force at different positions and the spring potential energy, while the relaxed spring length is important to calculating the spring compression S. Newton's second law is important to deducting the position of the weight on the spring, and the energy principle is important in calculating the value of the different types of energy at the different positions. The total energy remains zero, but is converted into different types, such as kinetic energy, gravitational potential, and spring potential energy at the different positions. The last step is to insert the observed position data to see how the predictive data compares to the observed data. Taking a look at the predicted data, the blue ball on the spring shows that it moves in a similar path to the observed position data, but does not line up exactly. The observed data moves a little slower than the predicted data, due in part to the start frame that I picked, as well as the difference in the spring constant I solved for. Taking a look at the position versus time graph shows that the predicted blue line and the observed red line follow a similar path, but in the ideal model, there is no account for dissipation of energy over time. Looking at just the observed red data shows that the amplitude of the spring starts to lessen over time as there is a loss of energy that is slight and is lost due to friction as the spring stretches, losing energy to heat, which is something important to consider for a longer time interval in non-ideal conditions. Taking a look now at the predicted data that is ideal, the essential question is the energy principle satisfied can be observed based off of the change in energy versus time graph. The total energy, the orange line, stays constantly zero throughout the oscillation time. Changes in energy within the system still add up to zero as there are no significant surroundings and the attachment of the point of the spring is fixed so that there's no work done by it, so that the energy principle is in fact satisfied. The other what does it mean question asks me to compare the period of oscillation for both the x and y data. It is important to consider which period of oscillation to use as the spring oscillates both vertically and horizontally, as both in spring motion and pendulum motion, where the source of oscillation is different for each dimension. To find the period of oscillation for both the x and y data, I took the average of the first 3 periods and found the period for the y data to be greater than the x data. The use of a larger number of oscillations allows for greater accuracy. While the motion isn't entirely vertical, I found it better to use the y position data period of oscillation, as the spring started off vertically stretched.